Flux density homework, problem 2, part 2. Now, we already calculated what's going to be the total charge present in the surface of our cylinder. If we recall, was 0.08 pi nanocoulombs. Now, we're going to calculate what's going to be the amount of flux leaving the surface defined by radius of 8 centimeters, the same that we did before. Now, C is going to be constrained not from minus L to L or from minus infinite to infinite, but from 1 centimeter to 5 centimeters. And the phi is going to be constrained by angles between 30 and 90 degrees. So let's go to it. First of all, let's go and change 30 degrees to a radian expression. And we're also going to call and to change 90 degrees to a radiant expression. How do we do that? Well, we know 30 degrees can be translated to radians by the application of radians equals to my angle divided by 180 times pi. For this one right here, we'll have 90 divided by 180 times pi. That means 30 will become 1/6 of pi. And 90, we already know it's going to become pi over 2. So instead of working with 30 and 90, we're going to work with 1/6 of pi and pi over 2. The integration we're going to use is exactly the same. We know the amount of flux is equal to the amount of charge contained in one section of the surface. In this case, the surface is going to be at a radius of 8 centimeters, but it's going to be constrained by an angle of 30 degrees. That's pretty much from here to an angle of 90 degrees. It's going to be pretty much in here. That means the surface part we're analyzing is going to be this one right here. We want to know what's the amount of flux that's leaving this surface. We go by the integration. Surface integration, double integration. One is going to be corresponding to C, one it's going to be corresponding to phi. The C is going to go from 1 to 5 centimeters, 0.01 to 0.05. The other one, is going to go from 30 degrees, that's 1/6 of pi, or pi over 6 to pi over 2. And my expression of surface distribution, which is 5 times e at minus 20 absolute value of c that we're going to calculate only with the positive c times the differential surface of rho that we know it's going to be of cylinder that we know it's going to be rho dphi dc, like that. We can replace the rho by 0.08, which is a fixed number where we know. And we can start simplifying the equation. We know 5 and this value are going to go out. That's going to give me charge or flux equals to 5 times 0.08 integration from 0.01, 0.05 integration pi over 6 pi over 2 of e at minus 20 c dphi dc. Once again, we got the integration about variable phi, but we don't have any phi. That means this integration will become only phi evaluated from pi over 6 to pi over 2. Flux to be equal to 5 times 0.08 times the evaluation of phi from pi over 6 to pi over 2. This one right here can actually translate to pi over 2 minus pi over 6. We can just replace it in here. And then we have the integration 0.01, 0.05, e at minus 20 c dc. And this integration where we know it. At the end, we will have an expression for my flux equals to 5 times 0.08 times pi over 2 minus pi over 6 times e over minus 20c evaluated from 0.01 to 0.05. Now, if we perform this evaluation right here, we will find out that the value for this is going to be 9.9, sorry, 442 picocoulombs. Well, actually, the value will be, remember, we're working with nanocoulombs from the beginning. So at the end, we will have 0.00942 nanocoulombs. However, that value can easily translate to 9.442 picocoulombs. And that's the answer for the part